Welcome to today's lesson on the importance of manipulating limiting factors in farming. This is an important application of the field of bioenergetics, applying our knowledge of limiting factors in photosynthesis. Today, we will explore the significance of manipulating limiting factors such as light, temperature, and carbon dioxide concentration to enhance the growth rates of plants in an agricultural context. We'll also discuss how farmers can optimize these factors in a cost-effective manner to achieve maximum crop yields while minimizing maintenance costs. So far, you have learned about how plants need specific conditions to grow quickly. Light, temperature, and carbon dioxide concentration act as limiting factors on the rate of photosynthesis. If there is not enough of any of these factors, the rate of photosynthesis can be limited. Understanding these limiting factors is critical as they play a pivotal role in determining plant growth levels. Building on this foundational knowledge, we will advance our understanding of how these concepts can be practically applied in farming. By understanding how to manipulate these limiting factors effectively, we can uncover strategies that not only improve plant growth, but also ensure that farming practices remain economically viable. Let's get started. To maximize plant growth and improve crop yield, it is crucial to understand and manipulate the key factors that influence the rate of photosynthesis, namely light intensity, carbon dioxide concentration, and temperature. Greenhouses allow farmers to control the growth conditions of their crops, which can significantly influence the rate of photosynthesis. By optimizing the levels of limiting factors, farmers can ensure their crops grow more efficiently, producing higher yields in a shorter amount of time. Let's take a closer look at each of the limiting factors. Light is one of the most critical factors for photosynthesis, as chlorophyll in plants absorbs the light energy from the sun and uses the energy to convert carbon dioxide and water into glucose. In a natural environment, light availability changes throughout the day and seasons. Early in the morning or on cloudy days, light might be a limiting factor. In greenhouses, artificial lighting can be used to ensure that plants receive a consistent amount of light. This is especially important during winter months or in regions with less sunlight. By using LED lights, for example, farmers can change the type of light to suit the specific needs of their crops, thus enhancing photosynthesis rates. Now, let's look at how farmers can regulate carbon dioxide concentration. Carbon dioxide is another critical component for photosynthesis. In the natural atmosphere, CO2 levels can fluctuate, potentially limiting photosynthesis. Inside a greenhouse, CO2 can be supplemented to optimal levels. This can be done by using CO2 generators or by allowing controlled ventilation where CO2 levels are monitored. Increasing CO2 concentration can significantly boost the rate of photosynthesis, leading to faster and more robust plant growth. Finally, let's take a look at temperature as a limiting factor. Temperature affects the enzymes that are used in photosynthesis. If the temperature is too low, enzyme activity slows down, reducing photosynthesis rates. Conversely, if it's too high, the enzymes can become denatured and function less effectively. Greenhouses can be equipped with heating and cooling systems to maintain an ideal temperature range for crop growth. Automated systems can adjust temperature settings based on the time of day and external weather conditions. Greenhouses therefore provide many methods of controlling the limiting factors of light, carbon dioxide concentration, and temperature. We have just looked closely at the ways in which farmers can manipulate limiting factors to enhance crop growth. However, while controlling these environmental factors can greatly enhance crop yields, it does come with costs. Energy expenses for artificial lighting, CO2 generators, and heating systems can be substantial. Therefore, farmers need to carefully balance these costs against the benefits of increased production and potential profits. There are ways to ensure the additional light, CO2 and heat supplied to greenhouses is done efficiently. These can include investing in energy-efficient lighting systems, such as LEDs, to reduce electricity costs while providing the necessary light for photosynthesis. Implementing CO2 monitoring systems to ensure that CO2 levels are kept at optimal ranges without excessive waste. Using insulated greenhouses and energy-efficient heating and cooling systems to minimize energy consumption whilst maintaining temperature. Furthermore, Modern greenhouses often use computer software and remote monitoring systems to optimize conditions. For example, sensors can continuously measure light, CO2, and temperature levels, providing real-time data. Automated systems can adjust greenhouse conditions based on this data, ensuring optimal conditions without constant manual intervention. Finally, data analysis helps farmers make informed decisions about resource allocation, further enhancing cost-effectiveness and productivity. Now, let's look at a practice question. You need to be able to answer questions using data to relate limiting factors to the cost-effectiveness of adding heat, light, or carbon dioxide to greenhouses. A farmer is experimenting with artificial lighting in a greenhouse to increase the yield of tomatoes. The greenhouse is divided into two equal sections, one without artificial light and one with artificial light. The farmer collected the following data over a growing season. Based on the data provided, does using artificial light increase profits for the farmer? Justify your answer with appropriate calculations. Pause here to have a go. Now, let's work through the question together. Firstly, we need to calculate the total yield for each section. To work out the total yield, we need to multiply the yield per meter squared by the total area of the greenhouse. The control section, with no artificial light, has an average yield of 3 kilograms per meter squared and a total greenhouse area of 100 meters squared. Therefore, the total yield is 3 kilograms per meter squared multiplied by 100 meters squared, which gives us 300 kilograms. For the artificial light section, the total yield is found by multiplying the average yield of 4 kilogram per meter squared by the total greenhouse area of 100 meters squared to give 400 kilograms. Secondly, we need to calculate the revenue, or the money made from sales, for each section. To find the revenue, we need to multiply the total yield by the selling price per kilogram. For the control section, we calculated that the total yield was 300 kilograms. The selling price is £2 per kilogram, so by multiplying these together, we get a total revenue of £600 for the control section. For the artificial light section, the total yield was 400 kilograms, which when multiplied by the selling price of £2 per kilogram, gives us a total revenue of £800. Next, we need to calculate the total cost of electricity for the artificial light section. First, we need to calculate how much energy was used in total. As we can see in the table, the artificial light section used 50 kilowatt hours per meter squared. Given that the total area of the greenhouse was 100 meters squared, by multiplying these together, we can determine that the total amount of energy consumed was 5,000 kilowatt hours, or kWh. Now, using the cost of electricity per kilowatt hour in the table, we can calculate the total cost of the electricity used. The cost of electricity is £0.10 per kilowatt hour. As we just calculated that the artificial light greenhouse used a total of 5,000 kilowatt hours, we can calculate that the total cost for energy is £0.10 per kilowatt hour multiplied by 5,000 kilowatt hours. This gives us a total cost of £500. Finally, we need to use our calculations to determine the net profit for each section. For the control section, there are no costs associated with the yield of crops. Therefore, the net profit that is made is the same as the total revenue, giving us a total revenue of £600. However, for the artificial light section, there are costs involved as calculated in part 3. For this section, the net profit is calculated by the revenue minus the cost of electricity. The revenue, as calculated in section 2, was £800. The costs were £500. Therefore, by subtracting the costs from the revenue, we can calculate that the total profit for the artificial light section was £300. Overall, in response to the question, we can conclude that using artificial light does not increase the profits for the farmer. The control section, without artificial light, produces a net profit of £600, while the artificial light section generates a net profit of £300. Although the artificial light increases the total yield of tomatoes from 300 kilograms to 400 kilograms, the additional £200 revenue generated does not sufficiently cover the cost of electricity, which is £500. As a result, the use of artificial light does not lead to higher profits. In fact, it results in a lower net profit compared to the control section. In summary, this lesson has taken a closer look at the photosynthetic reaction, focusing on limiting factors in the reaction and the need to balance costs in practice. By understanding and manipulating the limiting factors of photosynthesis, light intensity, carbon dioxide concentration, and temperature, farmers can significantly increase crop yields within greenhouses. The challenge lies in balancing the costs associated with enhancing these factors to ensure that the increase in crop production translates into greater overall profitability. Utilizing modern technology and data analysis can greatly assist farmers in achieving this balance, leading to more efficient and sustainable agricultural practices.